Is Sagittarius A star even massive enough for a supermassive black hole? Are there galaxies around the little red dots? How important is plate tectonics? And in Q&A Plus, what's the biggest showstopper for an interstellar crew? All this and more in this week's question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brains, write it down, I'll gather them up, and I will answer them here. All right, let's get to the questions. Nomad77. Considering our black hole is only 4 million solar masses, is it really supermassive? Well, compared to a stellar mass black hole, it is definitely supermassive. When a star with more than 20 times the mass of the sun goes supernova, it will leave behind a black hole. And those black holes will start out in this sort of 3 to 4 solar mass range and then grow from there. And so on the one hand, you have the ones that are 4, 10, 20, 100 at the most times the mass of the sun. And then you've got, the Milky Way is one, merely 4.3 million solar masses. You've got Andromeda's, which is about 100 million solar masses. But then we see examples of supermassive black holes out there with hundreds of millions, even billions of times the mass of the sun. So they can get very massive, but I still think that 4 million is a lot and qualifies as supermassive. The interesting sort of search is the ones that are in the middle, the intermediate mass black holes, the stuff that's in the thousands of times the mass of the sun. You would expect that those would be out there. And when you sort of consider the mass distribution that is very common, when you look at stars, there are a few stars that are very massive. Most stars are small. You would expect to see more of the black holes that are in that kind of middle range, but we don't. We see the ones that are a couple of times to 100 times the mass of the sun, and then we see the supermassive ones. But where are all the ones that are intermediate mass? Billions and billions of stars. Are the little red dots supermassive black holes inside galaxies? That does appear to be what little red dots are. There's been this ongoing scientific question about the little red dots since James Webb first discovered them. In fact, it was one of the most dramatic new things about the universe that James Webb had turned out. Like right now, if you said, what is the biggest thing that James Webb has found, it's the little red dots. And these are these weird, almost point source objects that are giving off an enormous amount of radiation, but it's all in the red. And they're seen within the first billion years or so after the Big Bang, and then we don't really see them after that. And whenever you see something that is giving off that amount of energy in a very constrained, very tight location, then you assume that it is probably, has something to do with a supermassive black hole. The size definitely matches. These things are in the order of tens of light years across. So they're very, very small. And yet they are pumping out enormous amounts of radiation. But there's one big missing problem. And that is normally when you see supermassive black holes, especially actively feeding supermassive black holes, they're giving off a lot of X-ray radiation. The accretion disk around the black hole is so compacted together that it's almost like the interior of a star. So fusion is happening around a black hole, just in the accretion disk. And that gives off X-ray radiation, and X-ray telescopes are the way we find many of these supermassive black holes. But these little red dots aren't giving off the X-ray radiation in the way that you would expect. And so there's been lots of other ideas. My personal favorite is that these are baby globular star clusters in formation. That would be really cool. But there's been a bunch of ideas. But recently, probably in the last couple of weeks, astronomers have found an example of a little red dot that is giving off some X-ray radiation. And what they think is happening is that these sort of new supermassive black holes are feeding on so much material. They're producing so much dust around them that the dust is obscuring our view into the X-ray radiation. We're seeing the red and the infrared light coming out of it, but we're not seeing the X-ray radiation that you normally associate with a supermassive black hole. So that's kind of the leading theory right now. And what's even more interesting is how the evidence is building for this idea of direct collapse black holes. So, one of the longstanding questions about the universe was like, what came first, the galaxies or the supermassive black holes at the centers of them? That, in one case, you could have this giant supermassive black hole and that could serve as a kind of anchor for other material to start to go into orbit around it. Or you could have like a whole bunch of stars, the stars go supernova, turn into black holes, the black holes find each other, they merge, the black holes feed, and you get this accumulation of black hole at the center of this galaxy at the same time that the galaxy is forming. And, there was like kind of like the bottom up versus the top down, and there was two camps. But the real kind of general consensus is that no, they go hand in hand. That isn't it weird that the supermassive black hole and the galaxy around it are kind of roughly similar to each other in scale. There's got to be some kind of relationship, but it is really starting to look like it's the black holes came first, and that there could be ways that you could get a black hole that is millions of times the mass of the sun, not by merging black holes, but just directly, that there's a giant cloud of gas and dust, some way of material gets funneled into this central area and it just turns into a black hole. And that would be groundbreaking. Like that would be Nobel Prizes if we can get to this place where they know this kind of thing for sure. But it's sort of where things seem to be indicating. So it's a really exciting time. Luis Carniero. About the invisible black hole in the Euclid image, will Euclid plus James Webb data force a revision of dark matter models, or could something unexpected emerge? Right, so the whole purpose of the Euclid mission was not to take this amazing image of the center of the Milky Way. It was to use this pair of instruments to map out the history of the universe, its evolution. So it has this visible light telescope, so very similar to the kind of observatories you're probably familiar with, and that allows it to measure the shapes of galaxies. And then it has this infrared instrument on board as well, which allows it to measure the chemical composition of these galaxies. And so it can put these two things together, and it can measure the shapes of the galaxies and the composition of the galaxies. And what astronomers are looking for is they're looking for gravitational lensing. So we know that when you have large amounts of mass in between you and something that you're looking at, then that mass acts like a natural lens that subtly distorts the pathway that the light is taking to get to you from those more distant objects. And so Euclid is doing this just giant survey of a huge swath of the sky, but it's taking long images, like it's really staring at each spot in the sky for long periods of time, long enough that astronomers can start to detect all of that warping caused by the matter that's out there. And that is the dark matter, right? The dark matter is invisible, and yet astronomers can detect how it warps stuff that is behind it. The example that I always use is that you're down at the bottom of a pool. You're laying on the bottom of a pool and you're looking up and you're looking at trees or people or whatever, and they're all, all refracting around, distorted, because you've got the water in between you and those people. And the dark matter acts like this thing that's warping the light that is coming to our eyes. And Euclid will allow astronomers to look back into time, because, of course, the farther away we look, the earlier we're seeing back in time, and really measure the concentration of dark matter at different points in the universe. Measure the influence of dark energy on the expansion of the universe at different times in the universe. James Webb is not a survey telescope, and so it can't do these wide field views of the sky. It can be directed at specific targets. Nancy Grace Roman is a lot more like Euclid. It's going to be doing these wide surveys of the sky. Vera Rubin is doing these wide surveys of the sky, watching how things change. So there's a bunch of instruments that are doing this same job, and they're going to try and all approach this problem from different perspectives. But Webb is when you found something unusual and you want to get really good images of it, you call on Webb. In the same way that you call on Hubble, right? Hubble is like looking through a straw. It doesn't have a very big field of view. And so when you've got a specific target, you want to look at a newly forming planetary system, you want to look at a very specific star, you call in Webb or Hubble. But if you want just a wide view of the entire sky, that's what you're doing with Euclid. And these surveys are going to help us understand what is the influence, what is the percentage of dark matter in the universe, how has dark energy changed over time, if at all. It's time to shout out the new patrons at the $5 level and above. Neuter Dude, Bruce Britton, Stefan Hutter, Robert Huffnagel, Neil P., D. Solomon D., Matthew Fuller, April Adams, Eric Schomer, Mohammed Zahilmi Echoes. Join our community at patreon.com/universetoday. Casey Villain, have we found evidence of plate tectonics on any bodies beyond Earth? Do we have any idea about how rare this geological phenomenon is? Do we have ideas about the role of tectonics in habitability? No, yes. Moving on. No, I'll give you an answer. So plate tectonics is unique on Earth. This is this idea that the Earth is broken up into these separate plates where they are floating on top. So there's sort of like the lightweight continents are floating above the heavier ocean plates, and so you get the subduction and you get this material going underneath other parts. You get earthquakes and all that and lava and all that kind of stuff, but you get this refreshing of the material on the surface of the planet, and it appears vital for the habitability of planet Earth. And that if you don't have plate tectonics, you have a place like Venus. Venus is called a stagnant lid, which means that it is this sort of entirely probably solid shell around the mantle on Venus. You don't get the plate tectonics that we have on Earth. And that instead, it's possible that you just get the entire surface of Venus just inverting itself from time to time. Like so much pressure, so much heat builds up, and the whole thing just sort of flips over, liquefies. It's a mess. And we don't see plate tectonics on Mars, and we don't see it on Mercury. And so those are the only places that we can compare here in the solar system. We see something kind of like plate tectonics when you look at some of the icy worlds out there. You look at Europa, you see these cracks on the surface. You look at Titan, Enceladus, Ganymede. So it might be that you have a very similar process on these ice worlds, but it's ice floating on water. But we don't have any evidence. We don't know what's out there around the universe. It could be that plate tectonics is very normal, that there's a certain size of planet, a certain distance from the star, certain composition of the atmosphere, and that gets you plate tectonics, and it's, there's one in every solar system. But it might be that it's incredibly rare, that there is some very specific recipe for the conditions on planet Earth that allowed us to have these plate tectonics. Is it important for life? It appears to be vital. Again, just look at Venus, right? Venus sucks. And part of it is that Venus has no way to sequester the carbon in its atmosphere. On Earth, we have life. Life forms biology. The biology sequesters carbon onto the surface of the planet. You get geology that is subducting, that is essentially pulling that material under other plates on planet Earth and sequestering that carbon away from the surface. And so you have this regulation of the amount of carbon that's available in the atmosphere and the amount of global warming, temperature rise that you get. On Venus, that process maybe never happened or stopped at some point in the ancient past. And so the carbon dioxide just built up in the atmosphere from the outgassing from volcanoes, right? Volcanoes are outgassing, and then nothing is soaking it back up again. And it just keeps building and building and building. And we actually talked about this earlier in this episode, how great those volcanic gases would be if they would build up on Mars. And yet on Venus, it's too much, right? You want to be able to dial that back. So you want the perfect amount. And it could be that just this process of tectonics, constantly sequestering, you get this cycle that's going on in the atmosphere of the planet and the surface. And that is what's necessary for habitability. Now, we don't know, and the universe has a way of showing us that things can be weirder than we had ever expected and still work. And so it might very well be that, in fact, we don't need plate tectonics, that there is a version of Earth that's at the right distance, and there's other mechanisms that sequester the carbon and allow for the cycle to happen that don't require plate tectonics. But it really does look like the plates are key. Could be that we have a large moon, that somehow the influence of the large moon nearby has helped create plate tectonics. Could have been that it was the impact when Theia crashed into Earth and created the moon, that shattered the planet's surface in a way that created the plates, and that kept on going forever. So, without another world to compare to, we just don't know the answer to this question yet. And figuring out if another world has plate tectonics is going to be a tricky move, right? We can barely detect the presence of these planets at all. The most advanced technology that we have for studying exoplanets is to be able to measure the composition of their atmosphere. But maybe from composition of the atmosphere, that will start to tell you whether or not there are these methane cycles, carbon cycles, on water cycles on these planets, and that could give you a hint at the habitability, or maybe even whether there's some kind of tectonic activity on them. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. And this week's bonus question: what is the biggest showstopper for an interstellar crew. And I'll put a link in the show notes. All right, those are all the questions that we had this episode. Thank you, everyone who put your questions into the YouTube comments. Everybody who joined me for the live show that we did, that this episode questions were recorded in. I'm going to give you something to just chill out and relax to in a second. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Carradine, Chuck Hawkins, Commander Baylock, Dark Finga, David Giltoday, David Matz, Enthrallo Reading and Math for Toddlers, Evan.pro, James Clark, Jeremy Mattern, Jim Burke, Marcel Smiths, Mike Parcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Rain Kaidu, Richard Williams, Sean Sargent, Stephen Money, Team 49, Telescopes Canada, Vlad Zeppelin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. So normally I give you some kind of rant, or I tell you about media that I am consuming, but now I just want you to look at a hummingbird. So these are some videos of some hummingbirds that my wife took in our garden. Enjoy, just chill, relax, just watch them quietly, contemplate nature, and we'll see you next time.